All right, in this lesson, we're going to be solving problems using permutations. In the last lesson, it was combinations. In this lesson, it will be permutations. Now, quick review of what those are. So first off, how do we write them? So you can write them in three different ways, just like the last one. I'm sorry, I only listed two, but there is a third way. So you could write it as NPR. You could write it as P with parentheses N comma R, or you could write it as P parentheses and then N on top, R on the bottom, like that. All of those are saying the same thing. We read it as N permute R. And remember, to permute something is to find all the combinations where order matters. And we'll talk more about that in just a sec. So in the example of 5p3, this is 5 permute 3. Okay, so out of 5 people, I am choosing 3 of them, and the order in which I choose them matters. Okay, great. This is the formula, just as a review. And then over here, I have some important notes. So first of all, the order in which you choose people matters. Next, permutations are always greater than equivalent combinations. So what that means is, in the last video, over here, I had the example 5C3. 5C3 is always going to be less than 5P3. R must always be less than or equal to N. And then you can often simplify a permutation by just using the fundamental counting principle or the multiplication rule. And again, we'll talk about this in just a moment. All right. So let's dive into some problems here. In the first example, it says how many 4-digit numbers with distinct digits exist in mathematics? All right, so a couple things. First off, 4-digit numbers. All right. That means I am looking for a number with 4 places, just like this. All right. The next thing I'm going to highlight is distinct digits. All right. That means no numbers are going to repeat. Distinct means unique. So I'm going to write myself a quick note. No repeating numbers. Okay, so the way I would do this um, is I would go through each digit and I would think of the permutation that I need in order to fill that spot. All right. So in the first place, the first one's kind of tricky because you got to remember that if we're talking about 4-digit numbers, this is a good example, 1,234. Okay. This is a bad example. All right. This is technically the number 345. I've written it with 4 digits, but we don't really write 4-digit numbers with zeros in front, so this is a bad example. Okay, so that means I know in the first spot there cannot be a 0, which means I have 1 through 9 to choose from in this first spot. So for the first uh, digit place, I have 9 different choices, and I'm going to pick one of them. All right. And because it says distinct digits, and because we're talking about uh, different 4-digit numbers, the order matters, right? The number 1,234 is not the same as the number 1,324, for example. Okay, so in the first spot, I'm going to do 9 permute 1. Okay, then I got to think of the next spot, all right? Now, the next spot, I'm going to allow 0 to be there, okay? But I chose a number already in the first place, and it has to have no repeating numbers, which means if I take out whatever number I chose in the beginning, okay, but I put 0 back in, that means I still have 9 choices. So we're going to do that, okay? And then for the third spot, I took a number out, so now I have 8 choices. And then in the last spot, I took a number out. So now I have 7 choices. Okay. And again, these are all permutations because the order in which I arrange these numbers matters. All right. So now if I were to do this, okay, I would end up with 9 factorial over 9 minus 1 factorial times 9 factorial over 9 minus 1 factorial times 8 factorial over 8 minus 1 factorial, and then times 7 factorial over 7 minus 1 factorial. Okay, I'm just using the formula up here. Remember where the first number is my n, and the second number, how many I choose, that's my r. All right, this simplifies a lot. Okay, this is 9 factorial over 8 factorial times 9 factorial over 8 factorial times 8 factorial over 7 factorial times 7 factorial over 6 factorial. So all I did was just simplify these denominators, okay? Now think about this. 9 factorial, that's 9 times 8 times 7 times 6 times 5, all the way down to 1. 8 factorial is the same thing, but we just started at 8 instead of 9. So it's 8 times 7 times 6. So they both have 8, 7, 6, 5, 4, 3, 2, and 1 in common. So they just cancel. So what that tells me is 9 factorial divided by 8 factorial must just be 9. Okay, and I went over that trick in another video. So if you're still confused on that, make sure you ask me in class. Same thing here. This is just going to be 9. All right. 8 and 7 both have 7 factorial in common. So this is just going to be 8. And then this one is just going to be 7. All right. And what I said up here, that these problems can often be simplified by using the fundamental counting principle. It won't always work, but in this case, this is just the multiplication rule, right? I just think through each digit, and I think through how many choices I have for each digit. So in the first one, I have 9 choices. In the second one, I have 9 choices. In the third one, I have 8 choices. And in the final one, I have 7 choices. So 9 times 9 times 8 times 7, I'm going to put that in a calculator. And I'm 4,536. All right, now for this next one. It says a student council with 10 members wants to elect a president, a vice president, a secretary, and a treasurer. How many possible results are there in this election? So we know this is going to be a permutation. And in the next video, I will explain more why it's a permutation. But for now, let's solve it using a permutation. I have 10 members to choose from, and I'm trying to fill 1, 2, 3, 4 different roles. Okay. So I'm going to say 10 permute 4 is going to give me my answer here. Okay, so I can use the formula. I'm going to use 10 factorial divided by 10 minus 4 factorial. This is 10 factorial over 6 factorial. And then remember, this is 10 times 9 times 8 times 7, and then it is also times 6, 5, 4, 3, 2, and 1. But the bottom is also 6, 5, 4, 3, 2, and 1. So the rest is just going to cancel out with the bottom. So I'm left with this. And if I put that in a calculator, I am going to get 5,040 different possible results in the election. All right. And once again, this right here is just the fundamental counting principle. All right. For the first role, the president, I have 10 people to choose from. Then for the next role, I have 9 people left. Then for the next role, I have 8 people. And then for the last role, I have 7 people left. So there are 5,040 different election results. Okay, let's look at the next one. It It says you remember that the first two digits of a 4-digit combination are 7 and 3, and that no numbers repeat themselves. How many possible ways are there to guess the two remaining digits? All right, so I want you to go ahead and pause the video, see if you can do this one on your own. I'm going to give you or first I'm going to give you a little hint, right? So there are 4 digits. 1, 2, 3, 4. And I know the first one is a 7, and the second one is a 3 already. So I don't know what this one is, and I don't know what this one is, okay? So I want you to go ahead and pause the video, try it on your own. I will give you the answer in 3, 2, 1. All right, so you should have gotten 56 different possible guesses that you can make. All right, and I went ahead and highlighted this right here. You have to remember that no numbers repeat themselves, all right? And that in the first two spots, I already took out 7 and I already took out 3, all right? Which means out of 10 digits, there are 8 choices left for this first one. And then out of 10 digits, there must be 7 choices left for this last one because no numbers are allowed to repeat. So what I did is I took 8 permute 1 and I multiplied it by 7 permute 1. I used my formula, I simplified, and it got down to 8 times 7. And once again, this is the fundamental counting principle. All right, I have 8 choices for this first digit, and I have 7 choices for this last digit. So 8 times 7, 56. Now, even though it can be simplified using this, I want you to get in the habit of using the permutation formula just so you know how to do it. Okay, let's look at this next one. This one's a little harder, all right? It says, suppose there are 4 physics textbooks, 6 math textbooks, and 2 chemistry textbooks that need to be arranged on a single shelf. How many possible ways can the books be arranged if all the same subjects need to be next to each other? Okay, now there's another one I'm going to have you try on your own, but I'm going to give you a couple things to think about first. So, first of all, we know that all the physics textbooks need to be together, okay? We know that all the math textbooks need to be together. So there's 6 of those. And we know that the 2 chemistry textbooks need to be together. So this is one way we could arrange our shelf. What I want you guys to think about is 2 things. First of all, this arrangement is not the same as this arrangement. So the order in which I group the subjects together, that's different. So these are not the same. So I want you all to think about that. The next thing I want you to think about is that let's say these are not all the same physics textbook, for example, right? So let's say I call this textbook 1, textbook 2, textbook 3, and textbook 4, right? This, so P1, P2, P3, and P4 is not the same or does not equal this, P2, P4, P3, P1. Those are 2 different arrangements, right? So not only can I arrange the subjects around, I can also arrange the individual books around within each subject. So that's what makes this problem a little more complicated. Like I said, I want you to go ahead and pause the video, try it on your own. I will reveal the answer in 5, 4, 3, 2, 1. All right, you should have gotten 207,360 different ways to arrange this bookshelf. Okay, now using our 2 hints, I've broken it down for you right here, okay? There are 4 physics textbooks, and you want to arrange all 4 of them. So 4 permute 4. There are 6 math textbooks, and you want to arrange all 6 of them. So 6 permute 6. 2 chemistry ones, 2 permute 2. But then remember, guys, you can also rearrange the order in which you place the subjects. You could do physics first, then math, then chemistry. You could do chemistry first, then physics, then math. So there are 3 subjects, and you want to arrange all 3 of those. So it's 4p4 times 6p6 times 2p2 times 3p3. I've used the formula here. I've simplified. And right here, I want you guys to pay attention to the fact that these 0 factorials, they all equal 1. So this is just 4 factorial over 1, which is 4 factorial. So really what you've got is 4 factorial times 6 factorial times 2 factorial times 3 factorial. And Desmos will actually do factorial in the calculator. So you could type all this out if you want. 4 times 3 times 2 times 1 times 6 times 5 times 4 times 3 times 2 times 1 times 2 times 1 times 3 times 2 times 1. Ridiculous, right? Just type this into Desmos and it should tell you 207,360 different ways. Okay? Okay, let's look at the last example, all right? It says 8 people are seated at a dinner table for a political fundraiser. You planned the seating arrangement. What is the probability that the vice president and the president end up sitting next to each other? Okay, we're going to talk about this in just a moment. There's a couple different ways we can look at this one. Okay, the answer to this question depends on whether or not the people are sitting in a circle or sitting in a row. All right. And it's not specified here, so I'm actually going to show you both ways. All right. So we'll do a row first because it's easier. Okay. You have 8 people. All right. And it says the president and the vice president in this political gathering, so I'll put P and VP, must always sit together. Okay. So this is kind of weird, but because these two people sit together, we're actually going to join them together. All right, and we're going to treat them like one person for just a moment, okay? So if we just treat them like one big block and we just look at the other seats, it means there's 6 other seats besides these 2, okay? And I can arrange those however I want. So, okay, I'm going to permute the rest of these 6 people. So there are 6 people. I want to arrange all of them. Okay, now I'm going to look at these 2 people and I'm going to say, now wait a minute. The president could be on the left and the vice president on the right. But another possible way is the vice president could be on the left and the president could be on the right. They could switch seats, right? As long as they're next to each other, I don't care what specific seat they're in. So within those 2 people, I actually have to arrange them as well. So there are 2 people there, and I'm going to permute both of them. Okay, now, what is interesting to note here is the specific seat every person is in definitely matters. However, where you put the president and the vice president does not matter as long as they're together. So this, with them in the middle, would be the same as with them on the end or on the other end. That doesn't matter as long as they're together. So I don't have to take into account that I could move those 2 all over the table. So it's really just this. All right. 6 permute 6. That is 6 factorial over 0 factorial. And then 2 permute 2 is this. So this simplifies to 6 factorial times 2 factorial. All right. And when I put that in a calculator, I get 1,440 different arrangements. Okay, now if I think about it like a circle, this is where it gets a little weird. All right, what I need you guys to recognize here is if you have a circle of 8 people, like that, all right, where 1 is in this top left spot, okay? This is the same as this arrangement here, and the same as this arrangement here. So if you pay close attention, I'm still highlighting that top left chair, and all I'm doing is rotating everyone around 1 seat, okay? Those are all the same arrangement because all the same people are sitting next to each other. They've all just rotated 1 seat. So I don't treat those as different. which means if you guys keep rotating, there are actually 8 different rotations that are going to be exactly the same. So 8 rotations are the same. Okay, so rather than do 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, 8 factorial, like a normal permutation, I'm going to take one whole set of 8 out. So I'm now going to do 7 factorial. So there are people that have devoted their mathematical lives to proving this problem. But just trust me right now, for a circle, okay, the number of people is equal to the total number minus 1. So you just basically take one person out and then you do the same problem. So even though there's 8 seats, I'm going to treat it like there's 7, okay? Now, within that 7, right, I know 2 of them must be grouped together because I always want the vice president and the president to sit together, all right? So that means it's a very similar problem to them sitting in a row, okay? If I group one of them together and treat them like 1, and I know now I'm working with 7 people, not 8, and I just grouped 2 of them together into 1, that means there's 5 remaining seats instead of 6. Even though, yes, I know there are 6 physical seats, for a circle, we treat it like it's 5. So this is actually 5 permute 5, okay? And then what we do is we multiply that by the remaining 2 that we care about. So 2 permute 2, okay? All right, so when I do this, I'm going to get 5 factorial over 0 factorial times 2 factorial over 0 factorial. This is 5 times 2 factorial, and I'm going to put that in a calculator, and when I get 240 different seating arrangements. All right, that's it for this lesson. Let me know, please, if you have any questions. These are kind of complicated.